Welcome dear learners. We are continuing with transition and inner transition elements. In this module, we are discussing the chemistry of elements of first transition series. These are the transition elements. These transition elements belongs to 4 different series as we are aware: 3D series, 4D series, 5D and 6D series, and in this module we are focusing the chemistry of 3D series, that is the chemistry of elements of the first transition series. The first transition series is also known as 3D series. The general electronic arrangement of the 3D series of element is 3D 1 to 10, 4s 1 or 2. The elements ranges from scandium with atomic number 21 and ends in zinc with atomic number 30. That is, the elements of 3D series are 10 in number and they are scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Now let us have a glimpse on the electronic arrangement, their physical properties like atomic weight, atomic number, etc. First of all, scandium. It appears to be dark grey in color, and scandium with atomic number 21. The electronic arrangement is argon core with 3D1 and 4s2 arrangement. It is a solid and the crystal structure is hexagonal. For titanium, the atomic number is 22. The electronic arrangement is argon core with the 3D2 and 4s2 arrangement in the outer shells. And for the next transition element, vanadium with atomic number 23, its atomic mass is 50.9. Electronic arrangement is argon core with 3D3 and 4s2 arrangement. It is also a metallic solid which crystallizes in body centered cubic arrangement. Another transition element is with atomic number 24, that is chromium. For chromium, the electronic arrangement is argon core 3D5 and 4s1. And it should be noted that this electronic arrangement is an exceptional arrangement that we discussed earlier. This extra stability of 3D5 arrangement lead to this exceptional configuration. We are anticipating an electronic configuration of 3D4 4s2 in the case of chromium, but we got this configuration 3D5 and 4s1. This is attributed to its extra stability. Its atomic weight is about 52. It is also exists as a crystalline solid, and that crystal structure is body centered cubic. Another transition metal belongs to 3D series is manganese with atomic number 25. The electronic arrangement is argon core 3D5 and 4s2 arrangement. It crystallizes in cubic crystal lattice with atomic weight of about 55. Iron is the another transition element belongs to 3D series with atomic number 26. Atomic mass is about 56. It crystallizes in body centered cubic arrangement. The electronic configuration shows a regular trend as in the case of the previous members. The electronic configuration is argon core with the 3D6 and 4s2 arrangement. Cobalt is another one, atomic number 27. Argon core 3D7 and 4s2 is its electronic arrangement. Again a crystalline solid which crystallizes in hexagonal arrangement. Nickel with atomic number 28 having electronic configuration argon core 3D8 and 4s2, and here nickel crystal exists in face centered cubic arrangement with atomic weight of about 58.7. Copper is another transition element. It appears to be nearly red in color. Almost all other metals appears to be dark grey in color, but copper has a slight red in its appearance. With copper with atomic number 29 has electronic arrangement 3D argon core with 3D10 and 4s1. Here also there is an exception from the anticipated electronic arrangement. The anticipated electronic arrangement for copper is 3D9 4s2 owing to the extra stability associated with the completely filled d subshell. Copper shows exceptional configuration, that is, this is anticipated configuration, this is the correct configuration. Exception is due to the extra stability of D10 arrangement. This is the last 3D series metal, 3D series transition metal, that is zinc with atomic number 30. Its electronic arrangement is argon core with the 3D10 and 4s2 arrangement. See this electronic arrangement, this is also 3D10 with the 4s2. Since the d subshell is completely filled, the properties of the metallic zinc is slightly or may vary from that of other 3D series of elements. That is, zinc nearly, the performance of the zinc as a transition metal is very poor. Now we are discussing the characteristic features of transition metal with the special emphasis to 3D series. First part, the variable oxidation state. We learned in previous class that transition metal has a characteristic feature of exhibiting variable oxidation state. The reason for the variable oxidation state is very feeble energy difference between ultimate and penultimate shell. The same variable oxidation state is exhibited by 3D series of metals. That is, here in the case of 3D series of metals, the variable oxidation state existence is due to the minute or negligible energy difference between the n-1 the shell and ns shell, that is ultimate and penultimate shell. Even though there are several oxidation states possible, lower oxidation states such as +2, +3, etc. are generally dominates over higher oxidation states. Oxidation states of 3D series of metals. This chart represents the lowest and highest oxidation state shown by each metals of the 3D series. Whenever we are taking scandium, the group number is 3. The lowest oxidation state shown is +2, the highest state is +3. But consider the case of manganese, which belongs to group number 7. The lowest oxidation state is +2 and the highest oxidation state is +7. Let us have some examples of different oxidation states of manganese. In the case of manganese, if I am taking MnCl2, manganese chloride, here manganese is present in +2 oxidation state. That is the lowest oxidation state shown by manganese. However, in certain coordination complexes, 0 state is possible. Some complexes like carbonylate anions, manganese may exist in negative state also. That is, manganese is a 3D typical metal which can show the possibility of different unusual oxidation states. What I am mentioning here is the most common oxidation state. +2 is the most common lowest state and +7 is the most common higher oxidation state. The most common higher oxidation state is shown in a compound, that is nothing but potassium permanganate. You are all familiar with its color also. Potassium permanganate is appearing as perfect violet or deep pink in its color, and potassium permanganate has molecular formula KMnO4. Here manganese is present in +7 oxidation state. That is, +2 state is the common lowest state of manganese and +7 is the common highest oxidation state of manganese. Whenever we are taking copper or chromium, we can see that the lowest oxidation state is +1. Why this +1 oxidation state? It is clear that chromium has an electronic arrangement 3d5 4s1. Whenever I am removing this 1 electron, we will get Cr plus state. So chromium exhibit chromium +1 state, that is the lowest state. Similarly for copper, 3d10 4s1 is its configuration. If you are removing the 4s electron, we will get to copper plus arrangement. Relative stability of different oxidation states. It is of no doubt that the relative stability of different oxidation state associated with stable electronic configuration. The electronic configuration or electronic arrangement such as D0, D5 and D10 configuration always have some extra stability. Therefore, a particular oxidation state with this type of electronic arrangement will be more stable compared to other oxidation states. For instance, if you are taking manganese 2 plus, it has an electronic arrangement of 3D5-4S0. D5 is a highly stable half-filled arrangement. That arrangement is more stable compared to manganese 3 plus, where the electronic arrangement is 3D4. 3D4 is comparatively unstable with the 3D5. Hence, manganese 2 plus state is more dominating over manganese 3 plus state. Higher oxidation state become less stable as the atomic number increases. This is the variation of oxidation state for the 3D series of elements. Now, the complex formation tendency. All the D block elements have the tendency to form coordination complexes. Coordination complexes are obtained by the combination of central transition metal or its ion with a group of molecules or ions or species called ligands. A ligand is a species which is capable of donating at least a pair of electrons. There are several types of ligand, and the 3D series of elements can form coordination complexes with the several kind of ligands, with the neutral ligand like water, ammonia, phosphine, with charged ligands like Cn minus, NO plus, etc. Several coordination complexes are formed by the 3D series of elements. The small size and high nuclear charge associated with 3D series of metals favor the coordination complex formation. Now, commonly observed geometries of the coordination complexes formed by 3D series of metals. The common geometries are linear geometry, square planar geometry, tetrahedral and octahedral geometry. This chart illustrates several examples for coordination complexes with the different geometries. For instance, these linear molecules or coordination number 2, molecules having coordination number 2 is given by metals like copper and silver in the form of CuCl2 minus, AgNH3 twice plus. AgNH3 twice plus has an IUPAC name of diamine silver 1 ion, and all such fragments are linear in shape. Another geometry is square planar. The square planar complexes are given by nickel, palladium, platinum, etc. or central metal, 3D metal with the D8 configuration in 4 coordinate complexes prefers square planar geometry. Tetrahedral is other possible geometry with the coordination number 4. Several tetrahedral compounds are also known from 3D series of metals. Some examples are CuCN 4 times 3 minus, ZnNH3 4 times 2 plus, etc. Another possible geometry, more commonly observed geometry, is octahedral. This octahedral geometry is a favorable geometry when coordination number is 6. Some examples are TaH2 6 times 3 plus, that means hexa aqua titanium 3 ion, VCN6 3 minus, CrNH3 4 times, Cl2 plus, etc. etc. So, these are linear geometry, square planar geometry, tetrahedral and octahedral geometries are the common geometries of coordination complexes shown by 3D series of metals. Now, the magnetic properties associated with 3D series of metals. As we all aware, magnetic properties arise due to the presence of unpaired electron. Unpaired electron can have 2 kind of motion as we mentioned in the previous classes. That spin motion as well as orbital motion both contribute towards the total magnetic moment, and the spin contribution is more dominating over orbital contribution, and the spin contribution we can calculate it as spin magnetic moment. The spin magnetic moment mu s is related to number of unpaired electrons. If number of unpaired electrons is equal to n, the spin only magnetic moment can be calculated by using the equation mu s equal to under root n into n plus 2 Bohr magneton, where Bohr magneton is the unit on Bohr magneton equal to EH divided by 4 pi mc. The divalent cations of the first transition series are paramagnetic except zinc 2 plus. What happened to zinc 2 plus? Why it is changed to a diamagnetic species? Definitely based on electronic arrangement. Zinc 2 plus is a D-turn system. We can see there will be no unpaired electrons. That is, zinc 2 plus is diamagnetic in nature. All other divalent cations are paramagnetic with slightly increasing, gradually increasing magnetic moment with the number of unpaired electrons. It is possible to calculate the magnetic moments of divalent cations of first transition series for their spin only value based on this equation. Let us have a trial on that. First of all, scandium 2 plus. How to calculate the spin only magnetic moment of scandium 2 plus? In order to get it, we have to write the configuration of scandium 2 plus. We have a scandium configuration 3D1 4s2. So, when it is changed to scandium 2 plus, the electronic arrangement is 3D1. That is, there are 5 d orbitals. The electronic arrangement is 3D1, and you can see the presence of one unpaired electron. That is, unpaired electron equal to 1. By using this equation, root of n into n plus 2 Bohr magneton, we will get a value root of 1 into 1 plus 2 Bohr magneton, that is root 3 Bohr magneton. Hence, the value spin only magnetic moment of scandium 2 plus can be calculated as 1.73 Bohr magneton. This is about the situation. Similarly, for different configurations, we can find out the magnetic moment. In the case of manganese 2 plus, the magnetic moment value will be the highest. That is, the divalent cation with the highest spin only magnetic moment among the 3D transition series is manganese 2 plus. How we can illustrate this? Manganese is having electronic arrangement 3D5 4s2. When it is changed to manganese 2 plus, we will get 3D5 4s0 configuration. If I am representing the electronic arrangement in orbital mode, this will be the arrangement 1, 2, 3, 4 and 5 unpaired electrons present in Mn 2 plus. That is, for manganese, number of unpaired electron will be n is equal to 5. Thus, the spin only magnetic moment root of n into n plus 2, that is root of 5 into 5 plus 2, that is root 35. Root 35 Bohr magneton. This is about 5.92 Bohr magneton. That is, manganese 2 plus is the divalent cation from the 3D series with the highest value of spin only magnetic moment. The spin only magnetic moment of some representative cations of the 3D series is shown here, and titanium 3 plus, the configuration is D1 and we will get a theoretical value 1.73, and for all such representative 3D series cations we can compute the spin only magnetic moment based on the equation root of n into n plus 2 Bohr magneton. But this observed magnetic moment may be slightly deviated from the calculated magnetic moment. The difference between calculated moment and observed moment is due to the fact that there may be orbital contribution. The orbital contribution is comparatively negligible with the when compared with the spin contribution. These are only spin components calculated. These are observed values. The slight variation between these two is due to orbital contribution. Variation of atomic radii of 3D series of metals. Here there is some decrease in trend from left to right, but for this series there is some irregularities observed. The values generally decrease along the series, but not a continuous decrease. The decrease is up to nickel, then slight increase to copper, then a sudden increase to zinc. that is there is some irregularities. These irregularities attributed to imperfect shielding effect. Variation in ionic radii of 3D series. With respect to the divalent cation, the variation in the ionic radii is shown here. The ionic radii shows a gradual decrease from left to right across the period. This decrease is connected to increase in nuclear charge from left to right across a period. Melting point variation is shown here. In the case of the 3D series of metals, lowest melting point is associated with the zinc and highest melting point is for vanadium as well as chromium. Ionization enthalpy, first ionization enthalpy values of the 3D series shows some irregular trend, whereas higher ionization enthalpies have regular trend. The appreciably high value of first ionization enthalpy of zinc is attributed to extra stability associated with electronic configuration of 3D 10 and 4s2. The ionization enthalpy variation along the 3D series is closely connected with atomic radii variation as well as shielding effect or screening effect. The second ionization enthalpy values show unusually higher values for chromium and copper. This is attributed to the extra stability associated with Cr plus, that is 3D5 arrangement, and Cu plus, that is 3D10 arrangement. Standard electrode potential is another part. Standard electrode potential of 3D series of elements has some regular trend, but this copper metal has positive value of its standard reduction potential, that is copper cannot liberate hydrogen gas when we put copper in dilute acids. This is because copper has tendency to get reduced, high tendency to get reduced when compared with the hydrogen, but all other metals has lower reduction potential compared with the hydrogen. Thus, when we put all other metals except copper in dilute acid, we can see the liberation of the hydrogen gas. Catalytic activity by 3D series of metals. We learned that several transition metals and their compounds have excellent catalytic activity, and we are outlooking the catalytic activity with a special reference to 3D series of metals. Some examples are here. Finely divided nickel, freshly divided nickel or finely divided very small pieces of nickel is used as a catalyst for the hydrogenation purpose. That is, we can perform reduction reactions using nickel. This nickel catalyst is highly useful in the hydrogenation of oils and fats. Manganese dioxide is a catalyst which catalyzes the decomposition of hydrogen peroxide. Hydrogen peroxide decomposes to produce water molecule and liberate oxygen. This reaction is catalyzed by MnO2. Titanium tetrachloride, simply known as the Ziegler-Natta catalyst, is highly useful in the polymerization reactions of alkenes. Vanadium pentoxide used in catalytic oxidation of SO2 to SO3 for the contact process in the manufacture of sulfuric acid. Iron is used as catalyst in Haber process. Copper acts as a catalyst in the manufacture of dichlorodimethyl This dichlorodimethyl on hydrolysis and polycondensation produces linear polymers or linear organosilicon polymers called silicones. So, this CH3 twice SiCl2 is a very useful compound for the preparation of organosilicon polymers. For preparing that CH3 twice SiCl2, copper metal can used as a catalyst. Copper and vanadium, mixture of copper and vanadium can be used as catalyst for the large scale production of the polymer nylon 66. Nylon 66 is a polymer obtained by the polymerization of hexamethylene diamine and adipic acid. Both contain 6 carbon atoms each and hence the name nylon 6,6. For the production of nylon 6,6, copper and vanadium mixture can be used as a catalyst. Ferric ion, Fe3 plus ion can catalyze the reaction between I minus ion, iodide ion and peroxide disulfate ion. So, there are several catalysts from 3D series. Metal as such or compounds of the metal can perform as good catalysts. Binary compounds of 3D series of metals. What are binary compounds? A binary compound is a compound which is comprised of only 2 elements. For instance, water can be considered as a binary compound which consists of 2 elements, say hydrogen and water. Ammonia, phosphine, arsine, etc., etc., calcium oxide, all are binary compounds. Okay. Thus, in the case of binary compounds, along with the transition metal, some other elements are also present. So, these binary compounds contain transition metal and other elements like oxygen, sulfur, halogen, etc. If oxygen is present, we will get oxide. If sulfur, we will get sulfide, so and so. That is, the common binary compounds of 3D series of metal include oxides, sulfides, halides, phosphides, carbides, etc. Then we are focusing the oxides first. Elements of the 3D series reacts with oxygen, atmospheric oxygen, to produce the binary compound oxide. This oxide formation or reaction of the transition metal with oxygen generally happens at a high temperature. Oxides may be of 3 types based on their nature. They may be basic, amphoteric or acidic. This is governed by the oxidation state of the central metal. That is, based on the oxidation state of the central metal, there are 3 kind of oxides from transition metals. They are basic, amphoteric and acidic. What are amphoteric compounds? They exhibit the properties of both acid as well as a base. That is, they can react with a base as well as an acid. Oxidation state proportional to covalent nature. Higher the covalent nature, higher will be the acidic nature. That is, higher oxidation state oxides have tendency to form acidic oxides. The 3 types of oxides are here. First one, basic oxides. They are formed by metals in lower oxidation state. These are ionic in nature. They are soluble in non-oxidizing acids like hydrochloric acid. This is about the general nature of basic oxides. Some examples include TiO, CRO, manganese oxide, FeO, etc. Another category of oxide is amphoteric oxide. They will exhibit the properties of both acid as well as base. They contain metals or transition metals in the intermediate oxidation state. That is, not low or not very high. They are also soluble in non-oxidizing acids like hydrochloric acid. Some examples are TiO2, VO2, Mn3O4, MnO2, etc. And the last category of oxides, they are acidic oxides. Acidic oxides are not heavily acidic, but they are slightly acidic, and these slightly acidic oxides are shown by transition metals with a very high oxidation state. For instance, vanadium pentoxide, here vanadium is present in its maximum oxidation state of +5, CrO3, where chromium has its highest oxidation state to +6, MnO3, manganese is in +6 state, Mn2O7, manganese is in +7 state. So, 3D series of metals with their highest oxidation state can form oxides with slightly acidic nature. About another category of binary compounds, that is halides. Halides are binary compounds of transition metal with the halogen, fluorine, chlorine, bromine, iodine. These elements of the 3D series combined with the halogen, preferably at a high temperature, yields metal halides or binary halides. The reactivity of halogen decreases from fluorine to iodine. That is, fluorine will immediately react with transition metal to form fluoride, but iodine, the rate of reactivity is comparatively very low. Owing to the very high electronegativity of fluorine, the reaction of fluorine with the transition metal will be very high. Fluorides are ionic, whereas other halides like chlorides, bromides, etc. are covalent in nature. For instance, some halides are here: TiCl3 titanium trichloride, TiCl4 titanium tetrachloride, etc. Another category of binary compound is sulfide. The combination of sulfur and transition metal produces binary compounds sulfides. Metal sulfides can be prepared by two methods. These two methods are: first one, the direct combination of metal, transition metal, 3D series of metal with the sulfur at elevated temperature. Second one is the reaction between transition metal salt solution either with hydrogen sulfide or with the sodium sulfide solution. These two methods are employed for the preparation of transition metal sulfides. Some representative examples are cobalt sulfide, cuprous sulfide, cupric sulfide, ferrous sulfide, etc. Another category of binary compounds are carbides. Carbides are the binary compound of carbon with transition metals or other elements. Metal carbides, preferably transition metal carbides, can also be prepared by two different methods. These are that methods: metal and carbon direct combination at high temperature is first method. Second one is the reaction between metal oxide with the carbon, that also happens at high temperature. In the second case, along with the metal carbide, some carbon monoxide gas will also be liberating. The carbides of 3D transition series can be classified into two types based on the force of attraction present in the carbide between the transition metal and the carbon. These two types of carbides are interstitial carbides and salt-like carbides. Let us go through the details of such carbides. Interstitial carbides, otherwise known as metallic carbides. They are very hard solids. They have high metallic properties like metallic luster. They are stable at a high temperature also. Chemically inert. Some examples are vanadium carbide represented by Vc, titanium carbide TiC, etc. Another category is salt-like carbide. These are ionic in nature because the name salt-like carbide also give an implication that the force of attraction present between the transition metal and the carbon is ionic bond. So, these are ionic in nature. These carbides are limited in number. They are limited to 3 metals from 3D series. The 3 metals that can form salt-like carbides are scandium, copper and zinc. On conclusion, we have discussed the general characteristics of 3D transition series, or the properties of the transition series are exemplified with respect to 3D series itself. Also, we considered the binary compounds of 3D series of metals like oxides, carbides, sulfides, halides, etc. for their general preparation methods and common properties. That all about this presentation. Thank you.